Welcome to lesson 58. You're going to begin this lesson actually with an investigation, followed by this lecture where we'll look at the properties of exponential and log functions, including their transformations. So let's begin by looking at exponential functions. They're always written in the form of y equals a to the power of x, where a can be any positive real numbers and a is greater than 1. You are encouraged to use your graphing calculator or Desmos to graph the following functions and compare the properties when we fill out this chart. I'm going to switch over to the Desmos app where I have input those equations. So first, we're going to start with the graphs of y equals to 2 to the power of x in red, y equals to x to the power of x, and y equals to 10 to the power of x in green. I have also included the horizontal asymptote of y equals 0, or the x-axis, on the graph. So as you can see, all three of these functions are always increasing, but they do not go below 0. It never crossed that asymptote on the x-axis, and they share a common point, the y-intercept on the y-axis at 1. For the next three graphs, we have y equals to half to the power of x, y equals to 1/5 to the power of x, and y equals to 1 over 10 to the power of x. You'll notice that the x-axis still serves as the horizontal asymptote, but in this case, all three graphs are decreasing. Okay, they are decays. So let's switch back to the lesson. So I'm just going to make a rough sketch of the graphs here because I'm not very good at sketching on the iPad yet. So to the power of x, I know that crosses the y-axis at 1. It's not really doing anything. Hold on. Okay, here we go. So at 1, and when x is 2, when x is 1, the y value is 2. Right. And then 2 squared is 4. 2 cubed is 8, and then so on, and -1, we can put this point here. So you notice how the decay kind of looks like. If I connect the dots carefully, something like this. Okay, so this is 2 to the power of x, and then we have the other two graphs that you can add on later. And let's sketch in the horizontal asymptote and label that as well. Okay, I will do the same for y equals to 1/2 to the power of x. It's pretty much the reverse in the sense that when x is equal to -1, you get 2, -2, you get 4, -3, it's 8, and then you get 1/2 here, something like that. Okay, so let's try this. Good enough. Okay, and then you can add on the other two graphs in your notes. More importantly, we're going to fill out this table. So the type of function that we see on the left, they are called exponential growth. And on the right, we have exponential decay. Intercepts, all of them have y-intercept at y equals to 1. And then for asymptote is a horizontal asymptote, but there's no vertical asymptote. Let's put down the equation. And is the function increasing or decreasing? Well, for an exponential growth, the function is always increasing. And for an exponential decay, the function is always decreasing. The domain and range of these two functions are both x belongs to real numbers, and the range would be any y values that are greater than but not equal to 0. Now, let's find the equation of the inverse function, okay, f negative 1, to this particular function, to the general form, a to the power of x. So if I let y to be f of x, then y is equal to a to the power of x. We're going to switch x and y to find the inverse. So x is equal to a to the power of y now. And you may remember, well, this is actually the exponential form of a log expression. So let's write this in log form so that y is isolated instead of x. So we can write this as log of x base a. Now, keeping in mind the domain and range of the original function, we know that, well, a must be greater than 0. And a base of 1 doesn't really make sense in here. So we'll set a not equal to 1 and x is greater than 0. We cannot log anything that is a negative. So we noticed how the natural logarithm, or ln x, is the inverse of the specific exponential function of base e. Later, we're going to look at the Euler's number e in greater depth. In this next part of the lesson, we will look at log functions. So once again, you can use graphing technology, Desmos graphing calculator, to graph the following log functions. I have already included that in Desmos, so let me get it out. So let me turn off the previous graphs and instead bring up log x base 2 and log x. So I hope this is not a surprise that instead of seeing a horizontal asymptote, it seems like there is a vertical asymptote now at x equals 0 or on the y-axis. Both of these log functions crosses the x-axis at 1 and 0. Okay. Now let's take a look at the other pair. This time, it almost seems like if I have a base that is between 0 and 1, my log function now looks like 2 decreasing function instead of 2 increasing functions. Okay. They still have a y-intercept at 1 and also a vertical asymptote along the y-axis. Okay, so I'm going to make a quick sketch of what we noticed. So there is a vertical BA at x equals 0. For log x base 2, there was an x-intercept. And when x is 2, this is 1. When x is 4, I have a value of 2. When x is 8, I have a value of 3. This is like the inverse, right, of the 2 to the power of x function. So if I sketch this nicely, negative 1's half, right? Okay, so something like this. So the function approaches the vertical asymptote on the left and continues to increase on the right. You can do better with that connection. And then for the second set of graphs, we have VA along the y-axis, x-intercept at 1, and then it's almost like the opposite, right? When I have 2, this is negative 1. When it's 4, negative 2, 8, it's negative 3, and when this is here, yeah, so let's sketch this. So I hope this shows clearly the function log x base 1/2, and this is y equals to log x base 2. Okay, so let's complete the chart. Intercepts. Where are the intercepts of these functions? Well, we have got 1, 0 for both. Both have a vertical asymptote of x equals 0. The graph on the left, this is an increasing function. The function on the right is a decreasing function. Domain is x greater than 0. And x is greater than 0. Range is any real numbers. And so you can recall the function transformations formula and apply mapping rule when you need to graph any version of these log and exponential function. So quickly recall, if I have this formula, when the horizontal stretch factor b is factored out, then the x values will be transformed based on x over b plus c, right? You move c units to the right if you see negative c in the equation, or if you see x plus c in the equation, then you move to the left, so it's a minus that number. And then for the y values, it will be ay plus d. You apply a and d as is. Okay, so let's take a look at some examples. In example 1, we are going to take the graph of f of x equals to 2 to the power of x, reflect it in the y-axis, and then translate by -3. So that means x, you go 1 to the left, and 3, you go 3 steps up. So write down the equation of g of x first. So let's take a look at this. So we have g of x equals, reflecting the x-axis is a vertical reflection. So that is applied to the function f. And then we're going to shift 1 unit to the right. So to the left. So we do x plus 1 here, and then plus 3 on the outside. The way this affects f of x, let's plug in 2 to the power of x. We have negative 2 to the power of x plus 1 now, plus 3. So what do we notice? We notice that this function has been shifted up by 3, which means that it affects the horizontal asymptote. Instead of being on the x-axis, it's going up to y equals to 3. The domain of g is still the set of x belongs to real numbers. The range of g is now the set of y that belongs to real numbers, such that y is less than 3 because there is a vertical reflection. Okay. If we use a table of values to compare the coordinates of f and the coordinates of g, let's make a t-chart. Okay, so for f of x and changing things into g of x, we have got the function 2 to the power of x. So when x is -1, y is 1/2. When x is 0, y is 1. So let's get a couple of these key points. 2 squared is 4. Okay. Now g of x, the x value is affected by the shift to the left. So we make everything one step to the left, to the left, to the left. The y value first will get multiplied by -1, and then we add 3 to that. So -1/2 plus 3, that's 5/2. 1 -1 plus 3 is 2. -2 plus 3 is 1. -4 plus 3, -1. Okay, so let's graph g of x. The grid is not the greatest, but it will do. Okay, so we have -1, 2, 0, 1, 1, -1, -2 is 2.5, something like that. Also, we said that the horizontal asymptote is y equals to 3. So here we go. Okay, so let's connect the dots as smoothly as possible. Okay, good enough. And here is g of x. Next, I see a familiar notation. I want to know the graph of p of x where it is f of the absolute value of x. If you recall from first year, when we see this notation, when we take f of the absolute value of x, what it really means is that you reflect any part that is greater than x, x equals 0, across over the x-axis, the y-axis, I mean. So let me write down this note. Right, because technically when you take the absolute value of x, any negative values of x ends up being, like, if it's x is -1, you're really taking f of absolute value of -1, which will have the same y value as f of 1, and so on and so forth. That's why we see this result. Okay, so we got a couple of key points already for the original function of y equals to 2 to the power of x, and they are 0, 1, 1, 2, 2, 4, and 8. Let's get one more point. Okay. And this part stays the same, right, for p of x. But then what we need would be these points also to the left of the y-axis, like that. So by connecting these points, you're getting the image. Oops. And so this is the function p of x. Okay. Let's take a look at a transformation of a log function instead. So here we have y equals to the negative log of 2x plus 6 base 3. I noticed that the 2x is not factored, so this can be written as negative log base 3 of 2 times x plus 3. So according to our knowledge of transformations, we know that the x value will be affected by 2. So x over 2, stretch. And then plus 3 means we're moving 3 to the left, so minus 3. The y values are just reflected over the x-axis, so negative y. And what is this based on? This is based on the function x equals to 3 to the power of y. It might be easier to think about it that way instead of thinking about the function y equals log 3x. So let's take a look. See how they're the same thing, right? Okay, so now you can pick your original points strategically, because when x is equal to 1, you have 3. 1 is equal to 3 to what power? 0. What's the next convenient number to pick? That would be powers of 3 for x, right? So I'm going to pick 3, because then y is 1. The next power, 3 squared is 9. Just like that. Applying transformation rules, 1/2 minus 3, negative 5/2, 0. 3/2 minus 3, negative 3/2, negative 1. 9 over 2 minus 3, 3/2. And then negative 2. Okay, very good. And then it might be convenient to include any asymptotes in the transformations as well. And we know that there's a vertical asymptote, and it is the y-axis at x equals 0. So now any x's will be shifted 3 to the left. So I know that the new VA will occur at x equals to negative 3. So let's sketch the graph first before stating domain and range. So first thing, I'm going to put in the VA. Here we go. And then the points, negative 2.5, 0, negative 1.5, negative 1. 1.5, negative 2. Okay, so it is a decreasing function. Okay, just roughly make sure things are proportional. And here, let's label this as y equals negative log of 2x plus 6 base 3. And we will state the domain and range of this function. Domain is any x value that belongs to real numbers such that x is greater than negative 3. And the range is any real numbers. There we go. Moving on to the last example in the lesson. Example 3. So here's a graph of y equals a ln of x over 2. So this is already, somewhat transformed based on the natural log function. We're going to sketch the absolute value of ln of x over 2 minus 1. So once again, this is good review from first year. The first part here, we have the absolute value of the original function. What does this mean? This means that anything that is below the x-axis will turn positive, right? Because of the absolute value. So that means reflect any part of y equals to ln x over 2 in the, oops, no, that doesn't make sense. So any part of that below the x-axis, okay, over the x-axis. It's a little redundant, but it will do. And then once we do that, the negative 1 here suggests that 1 unit down is what we translate. Okay. So let's do this in 2 steps. I'm going to use a lighter color, the red. I'll color code. So anything below gets reflected. So I'm going to take some easier points if I can find them. Okay, so this is good. 1 is about what? 1, 2, 3, 3 and something. 1, 2, 3 and something. That's good enough. Okay, this is a good point here. So I'm going to reflect this point up. So 1 and then 1, 2, 3. This point here, I think. Okay, so that gives us a decent shape. And of course, any part that was above the x-axis stays the same. So let me label this as the function y of the absolute value of ln of x over 2. And finally, we just have to take everything one step down. Let me use a solid color. So 1 step down. Very good. 1 step down here. Okay. Something like that. And then what's a good point to use? 1 step down. 1, 2, 3, 4, 5 here. And then this one here, I can put it something like that. Okay. And then let's get another point over here. So 3. Okay. So here we go. Good enough. And this is our final sketch. Y equals to the absolute value of ln x over 2 absolute and then minus 1.